أعوذ بالله من الشيطان الرجيم. بسم الله الرحمن الرحيم. الحمد لله والصلاة والسلام على رسول الله. نبدأ حل الكويز. طبعا إن شاء الله for most tutorials for most quizzes and homeworks, whenever we see students have some problems, I will do my best to make up some video tutorial using PowerPoint to make sure that people understand the concepts, because it seems from the quiz that I graded, a lot of you are missing the main concepts covered in the quiz. So let's start with the first quiz, and then I'll see the reaction or the feedback from you guys, and then we can adjust things as we go. This is the first problem, where what he wants you to do is to calculate the direction, or find out the direction of the electric field of the charge distribution below at points 1, 2, 3. So these are my charges. Let me just take the pen here. These are my charges. Okay. One of them is positive and one of them negative, and he wants you to find the electric field at this point, the electric field at this point, the electric field at this point. So now we know how to find the electric field. If I want to find the electric field due to this point, so all I have to do is just draw a line connecting these 2 points. So I wanted to find the electric field due to this charge, and then I come in here and I placed a positive test charge. So test charge small and positive. So what does that mean? That means positive or positive, the electric field will be directed away in this direction. I'm sorry, my hand is not stable, but it's just along the line connecting these two charges. Now the same thing for these two guys. If I wanted to calculate the electric field at point 1, then the direction will be this way, along the line connecting these two guys. Okay, and then it will be direct. So this, let's call this is E plus or E positive, and the other one is E negative. Now the resultant of these two vectors can be found by simply doing the the parallelogram. I'm sure you're familiar with it, and this will be my resultant. So the direction of the electric field at point 1, it's directed this way. Now for point 2, again, so the direction is done. For point 1 is done. Now for the direction at point 2, all I have to do again is place a positive test charge. And as you can see, a small test charge here, as you can see, in positive and positive, it will be directed this way, right? Positive and negative will also be directed this way. So that means what? That means the electric field at point 2 is also directed to the right. Okay. Now for point 3, I have to be a little bit careful here. Now point number 3 is not clear. In fact, I just checked the numbers, the choices, and by knowing that at point 1 and point 2 the electric field is directed to the right, I can find the solution, or I can find the solution without even doing number 3. But let's do number 3. Yeah. So if I place my test charge here, again positive and again small, the electric field due to this charge, due to the positive one, will be but it will be a small vector, because the distance is very, very big, and the electric field is 1 over r squared. Okay, so 1 over whatever the big distance, 1 over big is small. However, the electric field due to this negative charge will be bigger, because the distance is small. So that means what? That means this vector is less than this vector, hence the electric field is directed this way. Okay, so the direction, this is my direction of 1, 2, and this is direction 3, and hence what the choice, I don't have the choices with me now, but you can figure out the correct answer. Okay, so place a test charge there, and then I place, and of course the electric field this one, and the electric field this one, and that's the electric field. So from there I can find the electric field which is directed to the right, and I can do the same thing for Q2, except that it's wrong here, because this is both of them in this direction. So the second one is in the third one is again as I have indicated. All right. Now let's look at question number 2. Question number 2, he wants you to find the electric field. Again, let me find the pen here. Okay, the electric field at points A, B, C. Where is the electric field equal to 0? Okay, now you see that if you take A, B points, the points which are outside, A, B, and E, you immediately see you wanted to place a test charge, a positive test charge. That means what? That means the electric field here is this way due to this charge, and the electric field due to this charge this way. Let me see. So the electric field at point A will both be directed this way, because remember, you place a positive test charge at this point. So the electric field is not zero there. These two vectors will add up. Similarly, similarly, if you go to point B, the electric field due to the charge Q will be this one, and due to 4Q will be bigger than this one because the distance is smaller and the charge is bigger. So again, they add up regardless of whether they're to the left or to the right. So that's not equal to zero. Again, if you do the same thing for E, again, it's this way. You place a positive test charge here, that positive and positive will be repulsion, and positive and positive will be repulsion, so it's not equal to zero. If you go to the point C, however, if you go to point C, the electric field at point C, you see that the electric field is defined KQ over R squared. And at point C, the electric field due to this point, due to Q4, will be directed this way. And that's why I put positive. And the distance here is 1. Okay. And the electric field due to this one, which is located at distance 1, 2, 3, 4, 5, it's 5, but it's directed this way to the negative side. So when I subtract these, as you can see, it's not equal to 0. Okay. Now, if you look at the electric field at point D, however, okay, so the electric field at point D, due to this one, which is 2 squared, it's directed to the left. And due to 4Q, it's 1, 2, 3, 4, directed to the right. So if I place that 4Q divided by 4 squared minus Q divided by 2 squared, and as you can see when you do the math, you find that is equal to 0. The net electric field is equal to 0, so the answer is point D. Now, question number 3, I have an electron that gets into a region, a uniform electric field. So I told you the electric field is uniform. If the electron leaves the region at this point here, okay, as shown, which vector best represents the electric field? Okay, now I need to find what the electric field is. Now, if you look at this, you see that the path the electron follows is as this. What does that mean? That means if you think of this as a parallel plate capacitor, this will be the negative charge, and this will be the positive charge, or the positively charged plate, and that's the negatively charged plate. Okay. What does that mean? That means when I draw my electric field, you know how I do it. I just place a positive test charge, and then positive will be up, and negative and positive and negative will be attracted up. So that means the electric field is directed from positive to negative upwards, and that's your answer. Okay. Now, this question really shocked me because for those of you who did not answer this, because this was simply taken from the homework. Now, first he wants you to find, he gave you a parallel plate capacitor. He gave you the charge on each plate, which is 5 microcoulombs. And he gave you the area, which he said that it's a plate of sides 2 millimeters. So what does that mean? That the two sides are equal. That means it's a square plate. So to find the electric field, all you have to do is Q over epsilon 0A, and Q is in microcoulombs, 5, you have to multiply 10 to the times minus 6, so that you convert it to coulombs, and epsilon is known, and the area is 2 millimeters, so you have to convert it to meters and square that. From that you get the electric field. Once you get the electric field, then we know that the definition of the electric field is force over Q. So this means that the force is simply QE. But what's Q? Q is the charge, the moving charge. Some of you put Q as the charge of the place. That's not right, because we're describing the force on this charge Q. The charge of this is a proton, so the charge of the proton is given, and the electric field is given. So from here you can calculate the force. And if you know the force, then you can calculate the acceleration from the fact that F is equal to ma. Therefore A will be simply F over the mass of the moving charge, which is the proton, and from there you can find the acceleration, which as you can see is very big. And the second, after that, he wants you to calculate the time. Well, we know it started from rest, so I can go to my kinematics equation and say delta x is equal to V0 plus a half AT squared, and so V0 is equal to 0, and from here I can find T, which is 2 multiplied by this divided by A, and from here I can find the time is 5 times 10 to the power minus 9, which is nanoseconds. That's it. And as I said, I'm surprised that you guys, or most of you, did not get this, but I have no explanation for that. We'll discuss that in class, inshallah. Okay, the last question, in which he's asking you to find the electric field at points A and B, and then find the force. So if I want to calculate the electric field at point A, then what I have to do, I have to calculate E1, or the electric field due to point 1, and then which is simply equal to KQ1 divided by, remember, this is 10, so that's 0.15 or 15 centimeters, so 0.15 squared. Q is given, Q1 is given, okay, and this is given. So from here, now remember how I calculate the electric field. I calculate the electric field by simply placing a positive test charge here. Okay, since this is negative and this is positive, so the direction of the electric field due to point 1 will be this way, and that's what we mean by negative I hat. Similarly, for charge 2, because this is positive, this is negative, so it will be this way. I calculate it, and that's what we mean by it. So one of them is this way, and another one this way. So that means when I want to find the net electric field, I have to subtract, and that's what you see here, is that the electric field is simply this minus that, and that will give me the electric field at point A. Similarly, I can do at point B, first of all, so the point B is this one here. So I place my positive test charge here, which is positive, so that means the electric field due to point 1, due to charge 1, it will be this way. And this is negative as well, so it will be this way, and this is smaller because the distance is small. In fact, we'll calculate how big is it. But these guys both are along the positive I hat, as you can see, and then while these guys will subtract, these guys will add. So this will give me that, and again it's positive. So when I add them, I get the electric field is equal to 6,300. Now the interesting point is that if you compare these two, electric field at point A and the electric field at point B, and if you take the ratio, you see that it's almost 1. And of course, if you wanted to calculate what is before I go to the calculating the force, now you notice that it's, if you go in here and you go in here, the electric field is the same. Okay, it's approximately the same, right? And then the last point is that if the electric field, the force at point felt by a proton placed at point A is simply the charge of the proton multiplied by the force. Take this, so that is the same thing, and that's what you get for the force, which is something very small. And that's it for the tutorial. Good luck, and we'll talk about this more, inshallah.